Hello, so today we're looking at the vector, parametric, and symmetric equations of a line in R3 or in 3 dimensions. All right, so what are these different forms? That's the important thing. So I have them written down here. Whoops. What's happened? Or let's do that again. So I have the various forms of the equation of a line written here. So we have the vector equation of a line in R3, parametric form, and symmetric form. So notice that we have our direction vector m, we have our point on the line, then the parametric equation, our direction vector, is given by the coordinates m1, m2, and m3. Similarly, in the symmetric form, our direction vector is given by these coordinates m1, m2, and m3. And in this third case, we need to ensure that none of these values are 0, m1, m2, or m3 do not equal 0 because we're dividing by them. All right. Okay, so keeping this in mind, let's have a look at what questions were asked. All right, so given points A and B, find, vector equation of a line, parametric equation of a line, and symmetric equation of a line. First thing we need to do is find this direction vector. So let's do this. So again, we have 2 points, A and B. The easiest way to find a direction vector is to find the vector AB. So let's do this. So direction vector M is the vector AB, so B minus A. A little sloppy there. All right, so let's take this difference. So 1 minus -2 is 3. -2 minus 1 is -3. 1 minus 3, -2. So this is our direction vector, 3, -3, -2. So let's start with part A, the vector equation of a line. So R equals some point on the line. So let's take the point A. So the corresponding position vector is OA. So let's just write out the form. I'm getting a little sloppy here. Strange. Maybe that's better. Okay. Plus, so vector R equals a point on the line, position vector for that point, times our parameter times our direction vector. So in our case, our position vector for the point on our line, we can use A, so -2, 1, 3, plus a parameter T times a direction vector M3, which is 3, -3, -2. Good. And just for completeness, T is the element in the real numbers. All right, so now the parametric equation of a line. Let's make it a bit smaller so we can see everything. So now we're going to take this vector equation of a line and break it down into its components. So x equals -2 plus 3t. Y equals 1 minus 3t. And z equals 3 minus 2t. And again, t is a real number. C, symmetric equation of a line. All right. So for this metric equation of a line, think about solving for t for every coordinate in the parametric equation. So let's have a look. So we have, if we solve for t, from here. So x equals the first coordinate of a point on our line is x equals -2 plus 3t. Solving for t gives x plus 2 over 3. That equals, again, solve for t. From the y coordinate of a point on the line, we get y minus 1 over -3, and that equals, again, solve for t from the z coordinate of a point on our line. So we have z minus 3 over -2. And that gives us our symmetric equation of a line. We just set them all equal to 0, and we have it. Good. All right, so that just requires a bit of practice. All right, so number 2, let's have a look at this. Find the angle of intersection of the two lines. All right, well, let's think about this. Let's scroll over to the left. We have two lines. We'll find their angle of intersection. How can we do that? Well, one way of doing this is finding the vectors pointing in the directions of those lines and then finding the angle between those two vectors, or finding the normals. That's another way. It kind of depends on what form of the equation of a line we have. So if you had the Cartesian form, then maybe you would find, that's interesting. Then you would find the normals and find the angle between the normals. Now, if you have the vector, parametric or symmetric form of the lines, you can find, let's use different colors, you can find the direction vector for each. And then find the angle between the two direction vectors. So we're going to use the second method. We're going to find the direction vectors for each of our lines. All right, so let's give our lines some names. We'll call one L1 and the second one L2. Let's find the direction vector for L1. So that equals -4, -7, 3. So we're just picking off the values in the denominator. Direction vector for L2 is 3, 2, 4. Okay. And now we want to find the angle between these two vectors. So how can we do this? Let's use the dot product. This is a common technique, using the dot product, because we have two different ways to find the dot product, and they're both pretty simple. So we're going to do this first way. All right, so -4 times 3, we got -12, plus -7 times 2, which is actually -14. So let's put that in, -14, plus 3 times 4, which is 12. So our dot product is -14. So we're also going to calculate the dot product using this other method. So magnitude, product of the magnitude of the two vectors times the angle between the two vectors. And this is the part that's going to be interesting. All right, so let's find the magnitude of direction vector 1. All right, so 16 plus 49 plus 9 times magnitude of direction vector 2, so 9 plus 4 plus 16, all times the cosine of the angle between the two vectors. Your calculator, so 16 plus 49 plus 9, square root of that actually. It's actually square root of 74. Let's leave it at that. And then, let's see, 9 plus 4 plus 16, that's 29. Whoops, 29. All right. So those two values are equal. So let's zoom out and let's put all this information together. So the dot product of our two direction vectors, what we have is we have negative 14 equals square root of 74 times the square root of 29 times the cosine of theta. Let's solve for cos theta. Good, so negative 14 over the square root of 74 times 29. Okay. Let's punch that into our calculator and see what we get. A bit of a mess, I think. 14 divided by 24 times 29. All right, let's try this again. Let's do the denominator. I don't want to make any mistakes. So 74 times 29. Oops, 74 times 29. All right, so we have negative 14 divided by the square root of 2,146. Big numbers. Get the square root of that. Inverse times 14. All right. Whoops. So we end up with negative 0.3022. That equals, there's never enough room to do math, I find, for computations. So that's a cosine of theta. So let's take cos inverse. Oh, theta equals 107.6 degrees approximately. So let's go figure out what question we're asked. Find the angle of intersection of the two lines. All right, so therefore, including statement, therefore, angle of intersection of lines L1 and L2 is 107.6 degrees. Good. That required a bit of effort, but we got there. Quite a bit of space. All right. So let's have a look at this last question. So find the value of k such that the two lines below are perpendicular. All right. So again, application of the dot product. But first, let's pick a different color. Let's label our lines L1. Oh, it's bright. And L2. I think a little too bright for me. Let's find the direction vector of L1. K2, K minus 1. Direction vector of line 2 is M2, negative 2, 2, and 1. We're going to take their dot product because we know that if we take the dot product of two perpendicular lines, or two perpendicular vectors, sorry, we're going to end up with 0. So we're going to set our dot product equal to 0, and then we're going to solve for k. So first things first, let's find an expression for our dot product. I've plugged in our two direction vectors, m1 and m2. And now we can take our dot product and we get negative 2k plus 4 plus k minus 1. All right, let's simplify. When we get negative 2k plus 4 plus k minus 1 equals, how many k's do we have? Negative k. And plus 3, this equals 0. So looks like k equals 3. So therefore, the value of k, such that these two lines are perpendicular, is 3. Good. So we've used the dot product a couple of times, 2 different times, to find the angle between two lines and to determine the direction vectors for lines that are perpendicular. Well, this brings us to the end of our session. If you have any questions, send us a note at info@raisebymarks.com or give us a call day or evening, and we'll be happy to answer your questions. Thank you for watching. We look forward to seeing you again.